EC 201, lecture 32. So yesterday we were looking at alternative small signal models for the bipolar junction transistor, and we started off with what we knew, namely the hybrid pi model. This is the base, this is the emitter, and this is the collector. And the base current is IB, the incremental collector current is GM times the incremental base emitter voltage, which can also be written as beta times IB, right? And we saw that the current in the emitter must be IB times 1 plus beta, and from prior experience with networks, we observe that nothing changes in this network if I replace the resistor by a voltage source equal to IB times R pi, and then when you have a voltage source at the junction of several branches, you can push the voltage source through the junction. So what we had was, this is the emitter. What is the strength of this voltage source? R pi times IB, and the same thing here. Is that clear? And we again notice that a current source in series with the voltage source is equivalent to a current source itself, so we can eliminate this voltage source, and what we have is this network, which is electrically equivalent to the first network that we started off with, or the hybrid pi model. Alright? We also know that the current here is beta plus 1 times IB. So if you consider this branch, we see that the voltage across the branch is R pi times IB, whereas the current flowing through the branch is beta plus 1 times IB. So this can be replaced by a resistor of value R pi by beta plus 1. And what is that equivalent to? R pi is beta by GM. So the value of this resistor is beta by beta plus 1 times 1 over GM. In any transistor worth its name, the beta would be fairly large, which means that this resistor or this quantity would almost be equal to 1 over GM, but they are not the same thing. Please note that there is a factor beta by beta plus 1. And we defined 1 over GM to be Vt by Ic, correct? GM is Ic by Vt, so 1 over GM got to be Vt by Ic. So can you think of a neat relation for this quantity? Vt by the quiescent emitter current, because IC by IE is beta by beta plus 1. Does that make sense? So this is often called small r sub e, and Re is defined to be Vt by IE, where IE is the quiescent emitter current. So is this a small signal thing or a large signal thing? They're all small signal parameters. And just like how GM is defined to be IC by VT, and we know how the definition came about, we now also know how the definition of RE came about, and that is just a network manipulation of the hybrid pi model. So if I redraw it in a slightly different way, you can see that this is exactly equivalent to the hybrid pi model. You understand? All I have done is straighten this out and replace GM by beta times IB. RE is often called the emitter resistance it is not a large signal quantity, it is a small signal quantity and represents this chap here. Okay, it's that R pi pushed through the junction and is VT by, not VT by IC, but it is VT by IE. So this is useful in several situations. In a couple of examples, I'll show you where this is useful. I mean, look at the circuit and tell me the answer. For example, yesterday we saw the input impedance of a common collector amplifier. This is the incremental picture. This is R, and we wanted to find Z in. Yesterday we replaced the transistor by the hybrid pi model and found the input impedance. Let's try and use the new model that we have come up with and see if it's any easier. This is beta IB, this is IB, this is RE, this is the base, this is the collector, this is the emitter. Alright, what else do I need to add now? The resistor R goes from emitter to ground and I need to find Z in. So can somebody quickly tell me what Z in is looking at this diagram here? Look carefully. It is RE plus R times beta plus 1. Is it obvious to all of you? So you can see that using this model is reduced computational burden, but you know the original model wasn't too difficult to compute with either. And if you replace RE with VT by IE, which is 1 over GM times beta by beta plus 1, in this expression, you should get back the same expression that we got, the big expression that we got for the input impedance yesterday. So in that expression you will only find GM. Here you will find RE, and the two are related as shown here. So it's actually quite straightforward. Another example where this representation is useful is the following. Yesterday we computed the input impedance of the common base amplifier, and the incremental picture of the common base amplifier is the following. I in, and this is I out. Yesterday we put in the hybrid pi model and found the input impedance. Today let's try the same thing with this new model that we seem to have discovered, which is beta IB, IB, RE, and IN. This is the base, this is the collector, this is the emitter. We are interested in finding the impedance looking in here. And what is the impedance looking in here? It's simply RE, because this current source has both ends connected to ground. Okay, we are interested in finding this voltage. It's simply IN times RE, so Zn must be RE. And if you replace RE with 1 over Gm times beta by beta plus 1, you will get the same expression that you got yesterday. Is that clear? Fine. RE model was derived from the original model. It follows that the results you get with this model or that model must be the same if you have done the calculations correctly. And either model is okay, choose your favorite and go with it. That finishes the discussion on NPN transistors. And just like how the NMOS transistor had a complementary transistor, okay, and we saw how the PMOS comes about. It just comes about by taking the top two terminals of the 2-port as the common terminal. The same thing can be done with the NPN transistor, and it turns out that there exists a device like that. It's called the PNP transistor. This is the NPN transistor. We have another animal called the PNP transistor. And in case you haven't noticed, the direction of the arrow in the NPN transistor indicates the direction of flow of what current? Of the quiescent current. The incremental current can flow in any direction, but the direction of the arrow is an aid to memory and is indicating that the quiescent current flows from the collector to the emitter. And this is the complementary device. This is the PNP transistor. So in an NPN transistor, IC must be IS exponential VBE by VT. If VBE is even, I am neglecting the -1 there. PNP transistor, as the arrow indicates, the quiescent current flows from the emitter to the collector, and IC, which flows out of the collector, is also the form some IS exponential. If current has to flow from here to here, this terminal must be at a higher potential than this terminal, so it must be VEB the base current in the NPN transistor flows into the base, and IB is of the form IC by beta. So this is IC. So the base current is a small fraction of the collector current, and in an NPN transistor the base current flows into the base. In a PNP transistor, this is IC, the base current flows out of the base, and again IB is IC by beta. And just like what we had in the NMOS case and the NPN case here, the device is in the active region. If for the device to be in the active region, there must be some minimum voltage between the collector and the emitter. In other words, the collector must be above the emitter by some minimum voltage, and that minimum voltage is called the VCE SAT, and that makes sense because current is flowing in this direction. Now can you guess what it would be for the PNP transistor? The VEC must be larger than some minimum value. In other words, the collector must be at least some minimum voltage below the emitter. So you can think of this as VEC SAT, and in English it basically means that the collector cannot go below the base because we assume that VCE SAT is 0.65 volts, which is also about the same thing as VBE nominal. So VCE SAT being equal to 0.65 volts means that the collector cannot go below the base. In a PNP transistor, what happens? These three terminals, which do you think has got the highest potential? The emitter. What can I say about the collector potential? The collector cannot go above the base. If you want the transistor to be in the active region. And just like how the NMOS transistor and the PMOS transistor had the same incremental equivalent circuit, the NPN transistor and the PNP transistor will also have the same incremental equivalent circuit. So the first bias stabilization technique is all the emitters will go to the highest potential typically, so you call that VEE. There is nobody is going to kill you if you call it something else. So can you tell me what the quiescent current here is? Assume the transistors are both identical and have a current gain of beta. So can you tell me what the collector current here will be? Both these transistors are identical and have the same emitter base voltage. So both of them must have the same. The collector currents are the same. Let me call this IC. This must also be IC. If the collector current is IC, what must the base current be? This must, which direction? It's going out of the base. This current must also be IC by beta. So the two of them must come like this, and this must be 2IC by beta. IC plus 2IC by beta must be equal to I naught, which means that IC must be I naught divided by 1 plus 2 by beta. If beta is large, we see that IC is the same as I naught, and this is nothing but a PNP current mirror. And if you want to add an incremental signal, what you will do is the usual thing. So what is the quiescent potential at the collector of this transistor? It is IC times R. How large can I make R before this guy gets into the saturation region? What happens to this potential as I go on increasing R? It will go on increasing. As it goes on increasing, eventually what will happen? the transistor will get into the saturation region, and so the question is, how much can I increase R before the transistor goes into the saturation region? Very simple, it's IC times R must be equal to VEE minus 0.65 volts. Just like in the NPN case, the nominal emitter base voltage is taken to be about 0.65 volts. So the limit for R, which will just place the second transistor at the edge of the active region, is given by R is VEE minus 0.65 divided by IC. So the GM must be IC by VT, correct? And whether it's an NPN transistor or a PNP transistor, the incremental equivalent circuit is the same. So what will be the incremental equivalent circuit of this chap? Okay, I replace every transistor by everything by the incremental equivalent. So VE will go to ground. This capacitor will go away. This current source will go away. What is the incremental equivalent circuit of this chap? We have done this many times. What is this? 1 over GM, very good. And what is GM approximately? This is 1 over GM RB, and I replace the transistor with its incremental equivalent, which is the same as, so this is beta times 1 over GM. This is GM times, if I call this, this is GM times Vs. So what is the incremental gain? This is the incremental circuit. So the incremental gain is by Vs is minus GM R, just like what we had in the NPN case. There's nothing new at all. Alright? And what is GM? IC by VT. Try and just simply think about what is the maximum gain we can get out of this amplifier at all. If you want to keep I fixed, but we want to increase gain, the only thing to do is to go on increasing R. If I went on increasing R, eventually the transistor will go into the saturation region. So the maximum value of R I can choose is VEE minus 0.65 divided by IC. So the maximum gain is given by VEE minus 0.65 divided by VT. Now what is the moral of the story? If you want a large gain with a resistive load, you must have a large supply voltage, and this is the same thing that we saw in the MOS transistor case. And which means what now? How do we solve the problem of getting large gain without having a large supply voltage? We can have the active load. Instead of having this resistor here, you can replace it by an NPN current mirror, just like how we did in the MOS case. The current mirror is one example. The next example is if you wanted the same transistor to do both the amplification and the negative feedback biasing, this is one way where you measure the collector current This compares the collector current with the reference current and applies feedback at the base. The other thing to do is to compare the emitter current with the reference current and apply corrective feedback at the emitter itself. And this resistor string biases the base to some potential. Okay, so this is I naught. And a poorer cousin of this technique is what? Replace the current source with a large resistor. And what is the definition of large? The GMRE must be easier terms. GMRE must be much larger than 1 is equivalent to what? If the drop across this resistor RE is much larger than VT, where VT is the thermal voltage, then that's equivalent to saying GMRE is much larger than 1. The third bias technique is you compare collector current with the reference current and apply feedback at the emitter. So, okay, now you got to tell me the sign on the op amp. So, if this potential is rising, what does it mean? The collector current is too high, which means what about the emitter potential? Is it too high or too low? If the potential between the emitter and the base is very high, in the PNP transistor it will push more current. So if this potential is rising, it means that the emitter potential is too high and it has to be reduced. So what are the signs in the op amp? Minus and plus. And how should I choose VREF to make sure that the transistor is operating in the active region? VREF must be less than VB in the PNP case, because if you want the transistor to operate in the highest the collector can go is the same as the base potential. The last stabilization technique is to compare the emitter current with the reference current and apply correction to the if this potential is increasing, it means that the emitter current is too small, which means that the base potential is too high. So what must I do? I must reduce the base potential. And how is that possible? So what should be the signs in the op amp? Plus and minus. Great. After stabilizing the bias, we again realize that whether it's a PNP transistor or an NPN transistor, the incremental equivalent has to be the same, and in principle they are all equivalent to can be made an infinitely large voltage controlled current source. So, and if you just use this, the gain is poorly controlled and so on. So you can put this as the forward amplifier in a feedback loop and make all the four basic types of controlled sources where the control parameters are all independent of the device parameters itself. And the first one is the voltage controlled voltage source with a gain of 1, and the incremental picture is this. So this is VI, this is VO. What is this? This is the common collector amplifier done with a PNP transistor. The next thing is the voltage controlled current source, and that is the same. The incremental diagram will be the same thing, except that the output quantity of interest is this chap here, and if VI increases, this incremental current will be VI by R. Then you have the current controlled current source, and that is basically the incremental diagram is like this. I in, I out, okay, and this is the what kind of amplifier? Common base amplifier. And the last thing is the current controlled voltage source, and the incremental diagram must look like this. Alright, and what is VO? If GM tends to infinity, VO must be equal to IN times R. So this basically covers all the 4 types of devices: NMOS, PMOS, NPN and PNP, and all the basic single transistor amplifiers you can make with these devices. One little thing that I wanted to ask you people, I found nobody asked me this question. When we were talking about voltage control voltage source and the current control current source, I conveniently assumed all the time that the gain of the current source or the VCVS or the CCCS is always 1. I mean, how come we didn't try to realize VCVS with a gain of 2 or 5 or 6.12, or why only 1? Okay, let me give it to you as a challenge. Anybody who can come up with a single transistor amplifier with a gain VCVS with a gain more than 1,